Hello everyone, my name is Andrew Caratu. I am a instructor at MathTopia Academy, and today I'm going to present the last 5 problems in the 2025 AMC 10B. Alright, so problem 21. Each of the 9 squares in a 3 by 3 grid is to be colored red, blue, or yellow. So we have a 3 by 3 grid. And we are coloring it, like all of them, one of 3 colors, in such a way that every red square has an edge with a blue square. Every blue square has like an edge shared with a yellow square. Yellow square has an edge shared with a red square. So we're asked to find the number of different colorings, and if we have 2 colorings that like are rotations or reflections of each other, then they are actually the same. So how do we determine? It looks like there's a lot of possibilities here, right? Like if we have like 3 colors we can fill in 9 squares, that's 3 to the 9 total possibilities. So how are we possibly going to count all of them? Well, as it turns out, most of like the examples that we can construct out of the 3 to the 9 cases are not going to work because of the 3 like color touching rules, right? So for example, if I just put like red, yellow, blues like this, for example, just put them randomly, it's very easy to find an example of a color that doesn't like obey the rule. Like in this case, we have a blue here, and it says that a blue square has to be touching at least one yellow square, and it's not. So, right, none of these are yellow squares. So what we can actually do is we can like create a sort of chain, right? So we can just say, without loss of generality, just pick like one color in one of the corners, and then we can just keep saying, okay, well, this next square has to share an edge with a different square, and keep generating a chain and see where that ends up. So here we have a red square, and that red square has to share an edge with a blue square. So, for right now, we're not trying to count things rigorously. We're just trying to get a feel for like what exactly the structure of a square of this form would have to be. So, we have a red color, and then that has to be touching a blue color, so we put a blue color there. Okay, this blue color has to be touching a yellow color, right? So maybe we put yellow here. Okay, and then yellow, we have to put like a red somewhere. Maybe we put it here. And then a blue, we have to put it somewhere. Well, if there's a blue over here, then this blue is not touching any yellow, right? So that's not going to work. So we have to put a blue over here. And then we have to put a yellow over here, and then a red over here, and then a blue over here. And now we've finally finished constructing our chain, right? Because this blue connects back to a yellow from that we've previously already like written down. So this is kind of an interesting chain, right? Interestingly enough, we ended up stopping once we found a loop. And in fact, when you think about it, this loop always has to exist, right? When we have a red square and then we try to find the blue square next to it, right, which is guaranteed because of the rules, right? If you start at a red square and then you go adjacent to another square that's blue, and then adjacent to another square that's yellow, etc., red, blue, yellow, eventually, since there are only 9 squares in the whole grid, you have to come back to a square that you've already like been to, right? In the process, forming a loop that goes red, blue, yellow, and eventually closes in on itself. So the question is, what is the size of this loop, right? Well, of course, this loop has to be well, since it goes red, blue, yellow, like a red square, yellow square, red square, blue square, yellow square, and it finishes off with a yellow square, right, before looping back around to a red square. Clearly, whatever loop we find has to have a length of a multiple of 3, right? So 3 divides the length of the loop. But at the same time, if we checkerboard the grid, right, if we like label these squares black and the other ones are white, we go black, white, black, white, black, white, because we're traversing adjacent squares of the grid. So this loop also has to have length a multiple of 2. And if we put these together, right, combined with the fact that, of course, since there are only 9 squares in the grid, the loop has at most 9 squares in it, clearly this means the length of the loop that we find has to be 6. Um, and this is really interesting because there's only one possible loop of length 6 that we can draw in the grid, right? If we just in general try to draw like a loop of length 6 in a rectangular grid where we always try to go to adjacent squares, there's only one way to do it, and it's via a 2 by 3 rectangle, right? You can try different possibilities, like if you're not convinced, but it's just it makes a lot of sense. Obviously, if you try to like have a turn like this, the amount of steps it would take you to go all the way back around would either be too much, or if you turn right back on yourself would be too little, right? And if you go just one more step out and then return back to home base, then it's length 6. So basically, you're forced to have a loop that looks exactly like this somewhere in the grid, right? It could look like this. It could look like this. It could be here, or it could be this way or this way, right? It could be one of these 4 possibilities. In addition to that, it could be going in the clockwise direction or the counterclockwise direction. So what I mean by that is, like, for example, we could have red, blue, yellow, red, blue, yellow. And in this case, if we do like the path or the chain thing that we talked about before, we go red, blue, yellow, red, blue, yellow, red. We're going this way, the counterclockwise direction. But on the other hand, it's just as likely that we could run into a loop that's going in the clockwise direction. So how do we handle all of these cases, right? Where we could go in the clockwise or counterclockwise direction? The answer is we don't. We don't even need to think about it. And the reason why is because if we have a loop in the grid in any direction, any orientation, then via rotations and reflections of the grid, we can just orient it in like in this section of the grid, like this way, and in this rotation, right? Like let me show an example of that. Let's say we have a loop that's like this way and it's going counterclockwise, right? Then we could rotate the whole grid so that it looks like this now. Still counterclockwise though, right? We rotated the grid 90 degrees, and then we can just flip it across this axis. So like that, we can turn any grid into a grid where there is a loop going in the clockwise direction at the in the top 6 squares of the grid. So now we can just assume that that's the case. And this makes things a lot easier. Now we can actually really start counting the number of cases for the problem. So in particular, this loop, it could go like red, blue, yellow, or it could go blue, yellow, red, or it could go, yellow, red, blue, right? It all depends on what we chose for the first square of the grid, right? So I'm just going to say let's just write that down. We have 3 possibilities for the top left, and then this forces the other 5 squares in the top 6, right? So let's say we make this red, then that's forced to be blue, yellow, red, blue, yellow. Since, of course, all the colors are symmetric with respect to each other, we can just, without loss of generality, assume that we chose red here. It doesn't really matter for the rest of choosing these 3 squares down here. Okay, so there were 3 options for the top left square, and then that forces these top 6. And now we have to ask ourselves, how many ways are there to fill in these remaining 3 squares? Okay, so this is a little bit more of casework, but in particular, remember that every single square has to connect to like its next color in the sequence, red, blue, yellow, right? So for example, if this square was blue, then that would work because blue would connect to yellow, right? That would be very easy. But there are other things that could happen that would prevent it from happening. So, for example, if this square was red, then this is not a red square here. So this square would have to be blue. And then this square would have to be yellow. And then there's no red square for this yellow square to connect to, right? So this square can't be red here. Similarly, this square can't be blue because this is not a yellow square, so we have to make this square yellow, and then we have to make this square red. And once again, there's no blue square for the red square to connect to. So essentially, via trial and error on each of these 3 squares, we can see that this square is the most limiting. In fact, it's actually forced to be yellow. So so not only are these squares forced if you choose the top left square, but this square is also forced to be like yellow. Okay, now what about these 2 squares? Well, notice how this square in particular, we can make it red or we can make it blue, right? Because red instantly connects to the blue and blue connects to yellow. But what happens if we make it yellow? Then we need to make this square red. But then this square has no blues to connect to. So once again, it's impossible. So this square can't be yellow. It has to be red or blue. And finally, we can observe that no matter what color this square is, there are exactly 2 possibilities for what this square can be, right? So for example, if we made it red, then this square can either be blue to head into yellow, or we can make it yellow to head into red. We cannot make it red because there are no blue squares here, right? So no matter what, there are always going to be two possibilities for this square, and then after we choose it, there are going to be two more possibilities for this square, right? Because it can either go into this square or this square. Okay, so in total, that means that there are four more possibilities. And since we didn't, since we assumed without loss of generality, like for each of the three possibilities, that there are going to be these four cases, that just means that the total number of possibilities is going to be 3 times 4, which is 12. But of course, it's important to ask yourself, did we accidentally, double count here? Like, did we accidentally count this, like, two different grids that can both be rotated to be exactly the same? And the only way that this could happen is if a grid had two loops, right? Because if a grid has only one loop, then that loop is already here, right? So we already oriented it in a very specific way such that we can't rotate or reflect a grid to line up in a different way, right? Like if we have another grid, if we had, in theory, if we had two different ways to color in this grid with the loop in the top, right? Such that, we could rotate or reflect them to be the same, then that would imply there would have to be a different loop in the grid somewhere, right? Because after that rotation or reflection, there would have to be a different loop somewhere. And what you'll notice is that it's impossible for us to have two loops that are like this overlapping with each other. And the reason why is because whenever you have a loop, it's always forced that the middle two squares are the same. So in this case, we would have these two squares are the same, and then these two squares are the same. These are all the same color then. And that would obviously not work because, for example, in a loop, these two squares have to be different colors. So essentially, the only way that two loops can be compatible is if they're like this and like this. And in particular, since this loop is going in this direction, we see that this loop also has to be going in the same direction, right? They can't be going in opposite directions. So basically, the only possible grid we could have double counted is this one, where we had another loop going like this way. And if we fill in those squares, red, blue, yellow, we can see that it was only counted once, right? Because this grid, if we flip it so that this loop goes to the top loop, it's still the exact same coloring, right? So we didn't accidentally color it in twice, so we didn't double count anything. So no, the answer is not 11, it is indeed 12. So that is a little bit complicated, mainly because of the fact that rotations and reflections were considered the same. So we had to think about how we could rotate grids such that they lie on top of each other. But in particular, using this loop as like the main indicator of the orientation of a grid is very helpful because it's very difficult for there to be more than one loop in the grid. Okay. All right, now problem 22. So a 7-digit positive integer is chosen at random. What is the probability that the number is divisible by 11, given that the sum of its digits is 61? So I think this problem might cause a lot of panic at first because it's asking for two different like properties that if you were just trying to do one of them at once, it wouldn't be too hard, but trying to do both of them at once is a bit mind-boggling. So let me explain what I mean by that, right? If you have like a 7-digit positive integer and you need to pick the digits so that they sum to like say 20, right? That's you can do like an application of like stars and bars, right? Where you have like certain stars and bars. In particular, it would actually be more challenging here because it would have to handle, a digit instead of being any number from 0 onwards. It's limited at 9. But we actually don't even need to think about that really in this problem because if you'll notice, the sum of the digits being asked for here is actually 61, which is very close to the maximum that a 7-digit number can have, right? So 7-digit positive integer, it's at most 9999999. And in that case, sum of the digits is 63. So if our sum of digits here is 61, then in fact, this is really not like a combinatorial thing where we're like trying to look at all of these different possibilities. In fact, the number of possibilities is very, very small. So we're looking at a very small like space of 7-digit positive integers, right? Because we're looking for the probability the number is divisible by 11, right? Not among all of the 7-digit positive integers, but only among those whose sum of digits is 61. Among which, like, among the 7-digit positive integers, there are very few whose sum of digits is 61, right? So we can think about what a number whose sum of digits is 61 would look like, right? It could be like this, right? Where we have 6 nines and 1 7, or we could have 5 nines and 2 8s. And as it turns out, these are the only two possibilities. And the reason why is pretty clear, right? You start with the number 9999999, and you want the sum of digits to be two lower than this maximal sum. So you just pick two numbers to be -1, and if you pick two different numbers to subtract one from, you get two eights. And if you choose the same number twice to subtract one from, you just get a 7. So these are the only two possibilities for a number whose sum of digits is 61. So now we can just ask ourselves among these numbers, right? So we can think about how many numbers in total there are here, right? Which is actually isn't very complicated, right? Number of numbers that are 9999997, right? 6 nines and 1 7. That's just we 7 choose one ways to choose among which of the 7 digits the 7 goes. And similarly here, this is just 7 choose 2, right? You choose the two places where the 8s go. So among these numbers, right, we can add them up 7. This would be 21. We add them up. Okay, 28. There are only 28 numbers. And we just need to find the probability, like that if we choose one of those 28 numbers, that its sum of digits is, sorry, that it's divisible by 11. So, of course, at this point, you could honestly just write out the numbers and check manually. But we're going to try to automate the process a little bit more than that, right? Because there's actually a much simpler way to do it, and we just use the divisibility by 11 fact, which states that, well, when you have like a number, I mean, we can just take any sort of number, 143, for example. If you take the sum of the every other digit, right? So these digits, the odd number digits, you get like 4, and if you take the sum of the even number digits, you get 4. And if these are equal, then or they're the same mod 11, then the number itself is divisible by 11. So a longer number, for example, would be like if we had like 9,854, right? So in this case, we take the odd number digits, those are 14, and then the even number digits, those are 12. Uh, and this is not divisible by 11. But if I were to swap these two numbers, which like in this case, we would get the sum of digits would be like 13 and 13, right? Today would be the same. Okay, so just how does that apply to this problem? Well, we can imagine like what the sum of the digits of every other number would look like in this number. So in particular, because all of the digits are restricted to be like 9 or 8 or very rarely 7, the sum of the even like the sum of the odd numbered digits and the even numbered digits is very restricted, right? So we can think about what the between like we can bound what the sum of the odd digits and the even digits are, like both from below and above. So let me let O be the sum of these digits, right? So let me use a color. So O is the sum of, oops, O is the sum of these digits, right? This is O. And then E is going to be the sum of the even numbered digits. Okay. So what do we know about the bounds on O and E? Well, for O, we know that it's bounded, since there are 4 digits here, and they can all be at most 9, it's bounded by at most 36. And as for the lower bound, right, we know that the actual number only has 1 or 2 digits like below the actual maximum amount, right? Like what I mean is that the sum of the digits is 61 instead of 63. So we do like these two -1 subtractions from two of the digits. So if they're both from the odd numbered digits, then that lowers the sum of the odd numbered digits by 2, making it only 34. Okay, similarly, for blue, there are 3 of the digits, so it can be at most 27. And if we do the -1 subtractions of the digits from 9 in both in even numbered places, then its sum will drop to at least 25. So essentially, these are both between 34, 36, 25, 27 within a margin of 2. We know both of them. And this is very important because what do we need? We need for O minus E to be a multiple of 11, right? That this is what we want. We want 11 to be a multiple. So 11 divides O minus E. And as you can see here from what these two values are, it's very clear that the only possible difference that is a multiple of 11 that could be feasible here is 11, right? So, you know, it can't be 0 because the intersection of 34 to 36 and 25 to 27, those intersections, there's no common number between them. So O and E can't be the same, right? Also, O minus E couldn't be 22, for example, right? Because if this was at most 36, this was at least 25. That means the difference between them would have to be at most 11. So it cannot be any higher multiple of 11 or any lower multiple of 11. In fact, this has to be exactly 11. And as we just discussed, well, the only way that that can happen is if these two equality conditions are met. So O is equal to 36 and E is equal to 25. So all of the odd number digits have to be 9s. And then the even number digits can be anything that we want, basically. So we can just count like how many different ways. Well, for example, we could have like 997 in these three spots, or we could have 988. So in this case, there are three possibilities, right? Three choose one to choose where the 7 goes. In this case, there are three choose 2 possibilities. There are three ways to choose where the 8s go. So in total, we get that there are 6 like numbers that are divisible by 11, whose sum of digits is also 61. So now our answer is just going to be the number of numbers divisible by 11 and sum of digits is 61 over the number of numbers whose sum of digits is 61. And that's just going to give us 3 over 14. Okay.